this is Laura Alfred again, continuing our series on hydrostatics. This lecture is on stability. So as I mentioned at the end of the pressure and buoyancy lecture, that static equilibrium is not enough to evaluate how good a ship is. You really got to find out more about its stability. And what do I mean by stability? Is this really just what happens when the ship gets tipped over? There's two different major kinds here. We talk about transverse stability, and then we'll talk about longitudinal stability. So first up, transverse stability. Okay. What happens when the ship is heeled? And by heeled, this is side to side, like port starboard. Okay, so some big load comes along and pushes your ship down a little bit. What happens? Okay. As an example here, let's just take a block, right? It's just a block here, and it's got a center of gravity, it has a center of buoyancy, and you take your finger and push down on one side. What happens? Well, the block tips over, right? The center of gravity is not going to change, but the center of buoyancy will, because remember, the center of buoyancy goes back to the center of the underwater volume of the ship, or the block in this case. So the center of buoyancy has shifted, which now if we apply weight and the buoyant force to it, now it creates a moment, right? So it's no longer in static equilibrium. What happens? In this case, right, you can picture this in your head, right? The moment will take to try and push the block back upright, and it's stable. Hooray! Similar block, now we have, again, this is a tall, skinny block now. Do the same thing. Take your finger, go push down on one side. What happens? It tips over. Center of gravity does not change, but the center of buoyancy does. It shifts over. Put in our arrows. Now we have a moment. It's no longer in static equilibrium. But in this case, right, look at how the moment is. It's going to take it. It wants to take that block and continue rotating it counterclockwise here, and then causing it to be unstable. It's going to keep flipping over. So now this is an unstable block, right? Okay. Similar thing, you can do same thing with a ship, right? Here's the ship. You take it, center of gravity, center of buoyancy, heel it over to one side from a load or a wave, what have you. The center of buoyancy shifts, apply your loads, take a look at the moment. In this case, the moment acts to right the ship again, so the ship is stable. Okay, so initial transverse stability. I want to illustrate something called the metacenter. So you take the ship, right, and tip it over a little bit. And a little bit more, and a little bit more, and a little bit more. You can see that the B here is the original center of buoyancy. It's shifting over to this B prime here. Okay, you keep going, keep going. It turns out that the ship for small angles sort of follows a circle, and the middle of the circle is M. It's called the transverse metacenter. This is not a point that is actually on the ship. You don't build it. It is just a property of the ship. So it is an imaginary point way up high in the sky that the ship will rotate about for these small angles. Okay, so the metacentric height is the distance from the center of gravity G up to M. So GM, metacentric height. You also have the metacentric radius, which is BM, right? And going back to K was the intersection of the center line with the keel of the ship. So here, all of these values all sort of work together, right? So Km is the total distance between the keel of the ship and M, which is the metacenter. You got GM, KG, vertical center of gravity, KB, vertical center of buoyancy. All these work together, right? So if you have, if you've got four of them, you can calculate the fifth, that kind of thing here. These are all properties of the ship here. Calculating BM, so going back, right, so G comes from loading, the center of buoyancy comes from the underwater volume, and all that stuff. If you can calculate BM, then you know where M is, and then you can calculate K to M, and then you can back out GM, which is what we're after. So to calculate BM, it's the moment of inertia, transverse moment of inertia of the water plane divided by the underwater volume. So that goes back to those characteristics that we talked about in the geometry of ships lecture. So you see here, this is what it is. Those numbers you get out of your hydrostatics program, it will also calculate BM for you. So again, but this then, so you get a bunch of BM values for different graphs. Okay. So really what we're trying to get after here is we're trying to figure out a way to quantify stability, right? Like our little examples where we're pushing down on blocks is all well and good for the concepts, but we got to put a number with this stuff. So this is what we do. So we take this again. We take the ship, we tip it over a little bit, track where the center of buoyancy is shifting to. Okay, we stop at a given angle of heel. It's how much the ship has been tipped over to the side here. You add in force vectors here. So the buoyant force is acting up through the center of buoyancy, but it's not the original one, right? It's the current one, the B prime here. Then weight is acting down through the center of gravity here. The distance here, this to where you draw a line from G over to where the kind of new center line is, the line between the center of buoyancy, the current center of buoyancy, and M. Draw that over. You get a distance called GZ. That's the righting arm, right? That's the distance, the right angle distance between where the two forces are acting between. So that's GZ is the righting arm. Delta, with the weight of the ship, times GZ is the total righting moment, right? So now for small angles, like up to maybe 6 degrees, GZ is actually equal to GM times the sine of phi, which is the angle of heel. So you can imagine how if you have GM, if you can calculate that, right, for small angles, you can then know GZ, which is your righting arm. So there is your measure. GM is your measure of initial transverse stability here. GM is what you're trying to get to. Okay. So going back, how do you calculate it? Because again, going back to the picture earlier, KB, BM, KM all depend on the shape of the hull. It will be provided to you by your ship's hydrostatics curves, which come from a computer program. The kg, which is the vertical center of gravity, and gm then depend on the loading of the ship. So you have to calculate kg by weights and moments calculation, and then once you know that, then you can back out then what km is going to be. So here's a note, right? So if gm is greater than 0, your ship is stable because you have a positive righting moment. If it's 0, then it's neutrally stable, which means that it would tip over and it would just stay there. It wouldn't move. If GM is negative, then your ship is unstable and it will continue rotating in the direction that you have heeled it in. Okay, so that's for small angles. For large angles, that equation of GZ is approximately equal to GM times the sine of phi no longer holds. You have to do something different, right? So this is what I'm talking about. This was the initial transverse stability. For large angles, anything above 6 degrees of heel, this is no longer going to, this approximation won't hold. So you have to do a full-out calculation of it. So in your hydrostatics program, it will do this. It will take your ship and it will start to rotate it, and it will rotate, and it will calculate all the hydrostatics properties again, and it will calculate GZ for you. And then you can plot it all along this line. You can see how things are changing quite a bit, right? The center of buoyancy is moving way off the center line, and the geometry of the underwater part of the ship is really changed, right? So here the deck has gone underwater. And so when you come along. Finally, when G and B are on top of each other again, technically it is in static equilibrium, right? G and B are aligned vertically, so it's in static equilibrium. This here, this is then the range of stability. So like for this case, the ship has up to 52 degrees of heel that it is considered stable. So if it tips over that much, it will come back up to upright. If somehow it gets beyond the 52 degrees, it will capsize. So here you go. Now you can see that the moment is going the wrong way. The moment will now act to continue rotating the ship over, and it'll capsize. All right. So hydrostatics program, again, they will calculate your GZ curves for all different combinations of displacements, draft, trim, etc. I mean, this is a major calculation here, and computers are so wonderful at crunching these numbers for us. But you can get these, and then you can plot all of the different GZ curves, and so you have an idea of how is your ship going to behave in different conditions, different drafts, trims, and loading conditions and such. Okay, I do want to note that the initial GM has absolutely nothing to do with the rest of the GC curve. Remember, the GM is really only important for those really small angles of heel. Right, like I said, like less than 6 degrees here. Okay. However, it does have some influences on some other things. Okay, so for example, so here is a ship right here, a ship that has a large initial GM and a ship that has a small initial GM. This is just showing you kind of where things, how it might come about. A large initial GM is very good for stability, right? And the small initial GM is bad for stability, right? Because you don't have much wiggle room there. Here. However, a large initial GM actually gives you a short roll period. So I'm just going to kind of, if I get my hands, it's going to go short. Long roll period comes about from this small initial GM. So even though the small initial GM is bad for stability, it gives you this long roll period, which means the ship's going like this, which is kind of nice. So the short roll period it's very bad for comfort, right? I mean, just sit there and kind of do this with yourself. That's not so comfortable. And the high accelerations that can cause cargo to collapse or topple over, such that's bad. The long roll period is very good for passenger comfort, and the low accelerations are good for cargo as well. So if you happen to have a negative GM, this is the effect of it. So you have a negative GM, you have a negative initial GZ, which means it makes your GZ curve go negative at first, and it eventually comes back. But then you're trying to find this proper angle with the static equilibrium, and where it crosses the x-axis again there for GZ of 0. That's called the angle of lull. Right? It means you have a reduced range of stability here. So instead of going all the way from 0 degrees out to 55 degrees, you only get to go from 10 degrees up to 55 degrees where you're stable. Looking at it from both port and starboard here with these GZ curves, the areas where you've got inside that angle of lull means that the ship is going to slowly rock back and forth no matter what you do because of this negative GM here. So obviously this is not an ideal operating condition. We want to try and avoid that. Okay. Beam itself, the larger your beam, the larger initial GM you're going to have, and the smaller beam that you have, the smaller initial GM that you will have. Okay. Depth has an effect on stability as well. So remember, this is depth and not draft. This is actually depth. So as an example, take these two ships, ship A and ship B here. They have the same beam and the same initial GM, but ship B has a larger depth than ship A does. Okay, so we take them, we will tip them over a bit, right? Up until this point, they're behaving exactly the same. You can see their GZ curves are exactly the same. But now ship A, you can see its deck is about to be immersed in the water, and so now its GZ curve is now going to take a dive because of the seriously changing underwater volume, whereas ship B kind of keeps going along, so it has a higher GZ curve through there. And the result is that ship A has a lower or a shorter range of stability. It only goes up to 42 degrees, whereas ship B, because of its higher depth, can actually get up to 55 degrees. Okay. So taking into account beam and depth and all that stuff, this is what you want to try and do. You want to try and balance that initial GM stability from GM with the comfort and the low accelerations that you're going to need for your passengers and for your cargo. So you want to try and aim for this range of having GM be somewhere between 0.5 meter and 8 meters, depending on the kind of ship that you've got. Okay, so you've got here, what this means then is you either have a short, wide ship, or you have a taller, narrow ship. So again, if you've got a barge or something, you can get away with having a lower depth, lower freeboard, and still be in this happy range for GM. Whereas if you've got a narrower ship that maybe needs to be narrow because it needs to be faster, you're going to have to make it taller so that you still have enough GM to get in this sweet spot here. So that was just a real quick intro on transverse stability. Longitudinal stability, it has a lot of the same concepts, but in practice there's differences. So longitudinal stability is what happens when the ship is pitched. It means you press down on put your finger down, on the bow or the stern and see what happens with the ship. Just as with transverse stability, you have a metacenter, you have G, B, and you have K. And they're defined in exactly the same way. These are just the longitudinal versions here. Longitudinal BM here, again, it's defined the same except that now we're using the longitudinal moment of inertia on the water plane. Here, you can see how with the illustration here that there's a lot more area that's far away from the trim axis, which means that the longitudinal moment of inertia here is going to be a lot larger. The number is going to be much larger, and so the BM here is huge compared to the transverse BM. And so what happens then is you get this, right? So here's your ship, right, and here's the transverse version and the longitudinal version. BM is calculated the same way, but again, because the longitudinal moment of inertia is so much bigger than the transverse moment of inertia, it means that the BM of the longitudinal calculations is a lot larger than BM in the transverse calculations. So for transverse stability, capsize is a real danger here because BM is not that big. But for longitudinal stability, BM is just so large that it's almost impossible to capsize that way. So we don't worry about that so much, but we do worry about trim. So trim is the difference between the draft fore and the draft aft of the ship. It is a number. It's 3 inches or something like that. The ship rotates about its center of flotation, which is not necessarily at midships. Here, For zero trim, it's where the draft fore and the draft aft are the same. So trim itself is this lowercase t. It's equal to draft aft minus draft fore. If it's equal to 0, this is known as even keel or zero trim. Trim by the stern is often defined as a positive trim. Again, using this equation of the trim, lowercase t, is the trim aft minus the trim forward. So again, you get like heavy cargo in the back, it makes the bow pop up, and here's the difference. So this is trim by the stern. By the stern means the stern is down farther in the water. Trim by the bow now means that you've got the heavy cargo, whatever, is up in the front of the ship, and so by the bow means the bow is farther down in the water. This is often defined as negative trim. This is not an ideal operating condition, which is probably why it's defined as negative trim. We don't want to have negative trim. If you have to have trim, you want it to be positive. Again, just a quick review. Effects of the trim. It's applied to the drafts fore and aft according to where the longitudinal center of flotation is located. It affects all of the hydrostatic properties, so displacements, all the longitudinal, the center of gravity, center of flotation. So a lot of this stuff comes about, you have to iterate on things to make sure it all works out. And then the effects of all of that will be addressed in the calculation of weights and centers of the ship. Okay. So that is the quick intro to transverse and longitudinal stability. I hope that it helps. Now this is all well and good, but this is all if everything is okay with the ship, right? You haven't run into a rock or something like that. Damage stability is something totally different, and we will get to that in the next couple of lectures. But anyway, thanks as always for watching, and see you next time.